Hello, and welcome to section 4.4, L'Hopital's rule and indeterminate forms. In this section, we're going to go back to limits again, and we're going to look at a rule that we can use that involves differentiating to find limits. So because we'll be looking at finding limits again, you're going to need to remember some of those limit laws, or actually all those limit laws that we covered in section 1. Unit 1. And so just, if you're rusty on those, review these items. So this rule called L'Hopital's rule is used on limits that are called indeterminate. So there are certain limits that we couldn't find because we couldn't apply the limit laws that we'd learned. For example, the quotient rule, if the limit in the quotient is 0, we cannot apply the quotient rule. And there are some other results that are called indeterminate because it either leads to an ambiguous case or we're not sure just how to handle it. So when you have a limit that is going to result in something looking like this, these are called in some indeterminate forms. So if you try to evaluate a limit and you end up with 0 over 0 or infinity over infinity, or even one function's going to infinity and you're subtracting another function that's also going to infinity, yet these are examples of something called indeterminate forms. So we're going to use L'Hopital's rule on these 6 indeterminate forms. So let's look at a few examples of stuff that we've, shouldn't look too weird, that we've seen in the past that are actually indeterminate and that we've just found the limits like graphically in the past. The limit as x goes to 0 of sine of x over x is of the indeterminate form 0 over 0, because sine x is going to 0, obviously, as x goes to 0, and so is that denominator. So we can't use the quotient law because that denominator is going to 0. So we didn't know how to solve this unless we used something like the squeeze theorem or looking at it graphically. This limit as x goes to infinity of ln of x over x, that's of the form infinity over infinity, because ln of x is growing without bound as x grows without bound, right? And so is that denominator. But the thing is, we don't necessarily know that this limit's not defined, even though it's of this indeterminate form, because, depending on how these functions in the numerator and denominator behave relative to each other as x goes to infinity, that's what really determines what the limit is, the ultimate result. And then another example of the form infinity minus infinity would be this limit. So we're going to take a look at using L'Hopital's rules on functions, limits like that. So here is statement of the rule. A lot of people say la hospitals because it looks like the word hospital is in there, and this is French, and I don't speak French, but I've heard that it's not pronounced la hospitals rule, it's L'Hopital's. Another spelling you might see is without that S, but there's a little mark over the O, mark that looks like this over the O. That's another form of this spelling. Again, I'm no French expert, so I'll stop talking about that. But this rule is used when we have an indeterminate form of the form 0 over 0 or infinity over infinity. And it states that if you have a limit of to the quotient of functions, and the limit of the numerator is going to 0 and the limit of the denominator is going to 0, or the limit of the numerator is going to infinity and the limit of the denominator is going to infinity, and it could be either sign of infinity, then you can evaluate the limit of the quotient by taking the derivative, the limit of the derivative, the quotient of the derivative of each function. So this can be a little dangerous if you think back to the quotient rule for differentiation. Remember, when you find the derivative of a quotient, you don't just take the derivative of the numerator and the derivative of the denominator. There's that quotient rule. But here with L'Hopital's rule, in the context of finding a limit, that's exactly what you do. You take the derivative of the numerator and the derivative of the denominator. So make sure that if you're doing L'Hopital's rule for a while and then you need to go back to differentiation for some reason, you don't forget the quotient rule. So this is only used for finding limits of certain quotients, again with those conditions of 0 over 0 or infinity over infinity. And we're going to see that if we have a problem where we don't have a limit that meets those criteria, we can do some algebra to put it into the form where it will be 0 over 0 or infinity over infinity, and we'll look at examples. So here's an example from the text. Use the graph of f and g and their tangent lines at the point 2, 0 to find this limit. So I don't know what f is. I don't know what g is. I know what their tangent lines are. Those are the dashed lines here in the graph. And so to use L'Hopital's, we need to make sure the conditions are met. We have f and g are obviously both continuous from the graph. And since they're continuous, the limit as x goes to 2 of each of them is equal to, I can just evaluate the function at 2, because that's, remember, the definition of continuity. And so that limit is 0 in each case. So this does meet the criteria for L'Hopital's. So to find the limit as x approaches 2 of this quotient, I can find the limit as x approaches 2 of the quotient of the derivatives. So what's f prime and what's g prime? Well, remember, that's the slope of the tangent line, and we're given the tangent lines here. So the slope of the tangent for f is 1.8, and the slope of the tangent for g is 4/5. So then we have that this limit is 2.25. So this example involved remembering what the definition of a derivative was at a value, and remembering what the conditions are to apply L'Hopital's rule. Here's another example based on a graph. This time we have a function, just the graph of just one function, f of x, and its tangent line, y equals x, at x equals 0. So again, we can see that the function's continuous, and so differentiable on that interval. And since it's continuous, the limit as x goes to 0 of f of x is f of 0, and we can see from the graph that's just 0. Also, we can see the limit as x goes to 0 of this denominator, e to the x minus 1, is also 0. So we have the form 0 over 0. They're both continuous functions in the numerator and denominator, so I can apply L'Hopital's rule. So I take the derivative of f, and the derivative of that denominator is just e to the x. Now, what's the derivative of f of x at 0? It's just the slope of the tangent line at 0, and the slope of the line y equals x is 1. So this evaluates to just 1 over 1, because e to the 0 is 1. So my overall limit is just 1. Here's an example given, just a function, not the graph. So if you look at the numerator and denominator, these are each polynomial functions. They're continuous. So the limit as x goes to 1 of each of these is just found by evaluating each of them. So since the limit as x goes to 1 of this numerator is 0, and the limit as x goes to 1 of this denominator is 0, I can use L'Hopital's. And when I take the derivative of the numerator and the derivative of the denominator and find that limit, I get minus 1/3. So once you determine that the limit is, that you can use L'Hopital's on the limit, it's actually pretty easy if you remember the how to differentiate the functions in the numerator and denominator. So there are those other forms that we can use L'Hopital's on if we can turn them into this form of 0 over 0 or infinity over infinity. So if we look at this form, f of x is going to 0 as x goes to a, and g of x is going to infinity. So what does that mean? If g of x is going to infinity faster, then f of x is going to 0. This could be going to infinity. However, if f of x is going to 0 faster, this could be going to 0. So that's why this is called an indeterminate form. We don't know necessarily which function is going to have the greater influence in the limit. So here's an example of an indeterminate product. So the limit as x goes to 1 from the right of ln of x times the tangent of pi x over 2. So it's not a quotient, so I can't use L'Hopital's rule yet, but it is this indeterminate form. So I'm going to rewrite this in a way where I can use L'Hopital's rule. So remembering that tangent and cotangent are reciprocals, I'm going to rewrite this product as this quotient. And then it's in the form 0 over 0. So now I can use L'Hopital's, and I'm going to differentiate the numerator and differentiate the denominator and take that limit. And remember that these, remembering that these are each continuous and differentiable on around 1. So if I take the derivative of the numerator, I get 1 over x. The derivative of the denominator, I get minus pi over 2 times cosecant squared pi x over 2. And then I can evaluate that limit, and it's minus 2 over pi. So there's some other indeterminate forms that we also can use it on, and that's indeterminate differences. So again, if I have the limit of a difference of two functions and they're both going to infinity, they could remain close enough to each other that one their difference is limited. So this doesn't necessarily go to infinity. It doesn't go to 0, necessarily go to 0. Remember, infinity minus infinity doesn't make sense in the sense of a number. So it just depends on the functions. So again, we're going to try to use L'Hopital's rule by turning this into a quotient. So I'm going to find a common denominator and write this as a quotient. And when I do that, I make sure these are of course still continuous and differentiable. And I need to make sure that they're the form 0 over 0 or infinity over infinity, which it is. If I put 0 in each of those, I would get 0 over 0. So now I'll apply L'Hopital's rule, and I take the derivative of the numerator and the denominator, and I get e to the x minus 1 over e to the x plus x e to the x minus 1. And again, I end up with 0 over 0. So I can apply L'Hopital's one more time. I mean, you can keep applying L'Hopital's rule. I don't really know if there's a limit. But since this meets the criteria, we can apply it again. The moral of this story is don't worry about applying it more than once. And when I do that, my numerator's e to the x. My denominator is 2 times e to the x plus x e to the x. And now that, when I evaluate that at 0, I get 1/2. So now the third case is there's 3 different indeterminate powers. And that's, where we're going to have a function where we're finding the limit of one function raised to another function. So that's going to lead to these 3 indeterminate power forms that we can use L'Hopital's on. So if you think back to differentiation, when there was a function in an exponent, we would use logarithmic differentiation because that's how we get it out of the exponent and we turn it into a power. Excuse me, we turn the power into a product. So we're going to do that again. What we're going to do is we're going to assign a variable to the expression we're taking the limit of, f of x to the g of x power. We'll take the logarithm of both sides, and it doesn't really matter which one, but we take ln, just for convenience, remembering it's base e. And then using that power rule of logarithms, ln of y turns into this, g of x times ln of f of x. So if you look at this, this could be of one of those three forms, because g of x, if it was 0 to the 0, that means that the limit of g of x goes to 0, and the limit of the ln of f of x would go to minus infinity. So then this would be of the form 0 times infinity. Likewise, if this were of the form infinity to 0, then when I express it as a product, it's of the form 0 times infinity. And then lastly, if it was of the form 1 to infinity, then when I express it as a product, it's also going to be infinity times 0. So it doesn't matter which of these three indeterminate power cases it is, we're going to do the same thing. And we're going to look at that procedure in the next slide. But we have to fix the slide. I guess I can't go any bigger. So this is the first example of these other indeterminate forms. So the limit as x goes to 0 from the right of x times the square root of, raised to the square root of x. So this is of the form 0 raised to the 0. So again, this is an indeterminate form because, you know, this, if you look at it that one way, is it 0? You look at another way, is it 1? So, but what we're going to do is use the logarithmic procedure here. We're going to set y equal to this expression, x to the square root of x. We're going to take the logarithm of both sides and use that power rule of logs so that we have this product. So now that we're going to take the limit of both sides of those, the limit of the ln of y and the limit of this product. So this is in that 0 times infinity form. So we need to rewrite it using L'Hopital's. So if we rewrite the square root of x times ln of x as ln of x over 1 over the square root of x, then the limit as x goes to 0 from the right is going to be of the form infinity over infinity. So we can use L'Hopital's now that we've put it in this form. So we can differentiate the numerator and denominator, and I end up with the limit of 1 over x over minus 1/2 x to the minus 3/2. So if I simplify that a little bit, I end up with the limit as x goes to 0 from the right of minus 2 times the square root of x, which is just simply equal to 0. But we're not done yet, because remember, we took the natural log of y. We found the limit of the natural log is 0. This is a limit of the logarithm. We need to find the limit of the original problem. And we do that by remembering that we can express, you can always express any value as e raised to the ln of that value. So what I'm going to do is replace, I'm going to go back to my original problem. So I have the limit as x goes to 0 of x to the square root of x. And remember that you set that equal to y. So I'm replacing that with the limit as x goes to 0 of y. And I'm replacing that with this identity. So it's a limit of e to the ln of y. Now I did find the limit of the ln of y was 0. So because that exponential function is continuous, I can bring that limit in here. So this is e to the limit of the ln of y, which we just found was 0. And e to the 0 is 1. So this last step is it's a step of indirection, so it's a little bit, not about tricky, but you need to think about it a little bit extra deep, I think. So there's a lot of things involved in these steps. The logarithm of both sides, rewriting it so that it can be used in L'Hopital's, doing L'Hopital's, then remembering that you need to re-express it like this because you found the limit of the logarithm, not the limit of the original problem. So we have these other indeterminate forms, infinity to the 0 power and 1 to the infinity. Again, it's a matter, it's not, these aren't really the values that we're talking about. We're talking about functions that approach these values. It just depends which is approaching more quickly, which has the greater influence as we take the limit. So for another example, there's as x goes to infinity of x to the 1 over x. So here the base is growing without bound, so this x is going to infinity, and 1 over x, that function would be going to 0 as x goes to infinity. So I have this case, infinity to the 0 here. So we'll use that same procedure before and use L'Hopital's rule. So we do those 6 steps. We set y equal to the expression in the limit. We take the log of both sides. We use the product rule for logarithms. So this is of the form 0 times infinity. So we're going to rewrite this so that it's a quotient and meets the criteria for L'Hopital's rule. So if I rewrite 1 over x times ln of x as ln of x over x, that's pretty easy. This is infinity over infinity. Now we use L'Hopital's and differentiate the numerator and denominator. And taking that limit, I get 0. So now I need to remember that was the limit of the logarithm, not the limit of the original problem. So substituting e to the ln of y for y, I get e to the 0, which is 1. So that is the answer to the limit as x goes to infinity of x to the 1 over x. And then my last example of the other indeterminate form is of the form 1 to infinity. So you can see that this is an example of as x goes to 1, the base is going to 1, that exponent is going to 1 over 0 or infinity. So again, using the same procedure, set y equal to the expression, take the logarithm of both sides, and I have it in the form 0 times infinity. So I'm going to use L'Hopital's rule, and if I rewrite this as the ln of x over 1 minus x, then it's of the form 0 over 0. And I can use L'Hopital's and differentiate numerator and differentiate the denominator. I get minus 1. So my last step is to find the original limit by substituting e to the ln of y equals y. And I get my final, I get that is e raised to my limit I got here is e to the minus first, which is just 1 over e. So don't forget that if you have a quotient involved in a limit and it's of this, you need to check that it's of this indeterminate form, right? 0 over 0, infinity over infinity, before you can just apply L'Hopital's rule. And a lot of times you need to do some preliminary algebra if it's of one of these other forms to use L'Hopital's rule. And then these 3 special cases, which are a little bit trickier because you need to use the logarithm, and that final step when you reintroduce y to get the limit, you need to take some care with that.